Hello there. Thanks for joining us today. I've had a chance to look over your portfolio and your experience over the last 4 years, and it looks like you've had a really diverse range of projects. To get us started, why don't you just give me a high-level overview of your recent work and where you feel your strengths lie in the animation and VFX pipeline?
Thanks for having me. It's a pleasure to be here. Over the last 4 years, I've really focused on bridging the gap between high-end artistic intent and technical execution. I've spent a lot of time in the trenches of character animation and FX, but as I've progressed, I've found myself moving more into the architectural side of the pipeline. I've spent a significant amount of time optimizing systems to make sure the artists aren't fighting the software. For me, the sweet spot is where complex simulations meet performance budgets. I love the challenge of making something look physically believable, whether that's cloth, fluids, or complex rigging, while ensuring that the scene actually renders in a reasonable amount of time. I've also taken on a mentorship role with our junior artists, helping them understand not just how to push the buttons, but why we choose certain technical paths over others to maintain consistency. Across a feature,
That's a great transition into some of the technical specifics. Since you mentioned the balance between quality and performance, let's talk about the baking process. For a junior artist, it might just seem like a button they press, but from your perspective, how do you explain the baking process and why it's so critical in a production environment?
I usually describe baking as the process of permanently applying the effects of simulations, calculations, or procedural animations directly to the keyframes or geometry of an object. In a heavy scene, you might have a character with complex cloth or a procedural wind effect. If the computer has to recalculate those physics every single time you scrub the timeline or hit play, the viewport becomes unusable and the render times skyrocket. By baking, you're essentially storing the final result into the animation data. I like to use the analogy that it's like pre-cooking a meal. You do the hard work of preparation and cooking once, and then when it's time to eat, or in this case, render, you just heat it up. You aren't preparing the ingredients from scratch every single time. It's a fundamental step for efficiency, especially when moving assets from a simulation package into a final animation or rendering engine.
Right, it's all about stability and speed. Speaking of rendering, I want to dive into look development. There's always a bit of a tug-of-war between PBR workflows and traditional look dev. In your experience, what are the actual trade-offs there? When do you push for one over the other?
It really comes down to the goal of the project, consistency and realism versus creative flexibility. PBR, or physically based rendering, is fantastic because it simulates how light interacts with surfaces based on real-world physics. We use standardized maps like roughness, metallic, and albedo. The huge advantage here is consistency. If I build a PBR asset, I know it's going to look correct whether it's in a sunny desert scene or a dark interior, because the material properties are grounded in physics. However, the trade-off is that PBR can be computationally expensive, and it can sometimes feel restrictive. If a director wants a very stylized, exaggerated look that doesn't necessarily follow the laws of physics, PBR can actually get in the way. That's where traditional look development comes in. With traditional methods, we can manually tweak shaders and textures to achieve a specific artistic mood without being boxed in by physical accuracy. It's often faster to iterate on for stylized pieces and allows for those unique, non-photorealistic effects. But the downside is that those assets often don't translate well across different lighting setups. You might spend hours getting a look perfect in one shot, only to find it looks completely broken in another. So for a photorealistic feature, I'm pushing PBR every time. For a highly stylized short or a commercial with a specific vibe, I'm more open to traditional look dev.
Let's shift gears to physics. Cloth is notoriously difficult to get right. Walk me through your process for achieving a believable simulation on a flowing cloth object. What are the steps you take from the initial setup to the final polish?
Believable cloth starts with the foundation of the mesh. I treat the cloth as a grid of interconnected particles or vertices. Each of these is influenced by external forces, gravity, wind, and collision volumes. The simulation then calculates the movement of these particles over time, using equations that mimic real-world physics. One of the most important parts of the process is applying constraints. If you don't have proper constraints, the cloth can stretch like rubber or tear in ways that look unnatural. You have to define the structural integrity of the fabric. Once the basic physics are running, the real work is in the fine-tuning. I adjust parameters like stiffness, damping, and friction. This is where the material identity comes in. If I'm simulating silk, I want low stiffness and high fluidity. If it's denim, I need much higher stiffness and more friction to create those heavier, stiffer folds. It's a very iterative process. I'll run a few test sims, look at the way the folds break, and then adjust the mass or the damping until it matches the reference footage. It's all about balancing the mathematical model with the visual expectation of how that specific fabric should behave.
You mentioned the mathematical side of things. I want to dig a bit deeper there. For someone at your level, I'm interested in the underlying principles. Could you compare mass spring systems and finite element analysis in the context of cloth?
Definitely. Those are the two primary mathematical engines we see in cloth simulation. Mass spring systems are the more common, lightweight approach. They treat the cloth as a network of point masses connected by virtual springs. We use Hooke's law to calculate the force based on the spring's stiffness and how far it's been displaced. It's computationally fast and great for real-time or fast iterations, but it has a ceiling. It struggles with complex deformations and can sometimes feel a bit springy or unstable if the forces get too high. Finite element analysis, or FEA, is a different beast. Instead of just springs, FEA divides the cloth into small, discrete elements and solves partial differential equations to model stress and strain across the entire surface. This allows for a much more accurate representation of bending and shearing. If you need a shot where the cloth is being crushed or folded with extreme precision, FEA is the way to go. The catch, of course, is the computational cost. It is significantly heavier and slower to solve. Both methods rely on numerical integration, like Euler or Verlet integration, to update the positions of the vertices over time, but FEA gives you that higher fidelity physical accuracy at the cost of render and sim time.
That's a solid technical breakdown. Now, let's talk about the big picture. Imagine you're managing a scene with multiple high-complexity elements, maybe a character in the foreground, a massive explosion in the midground, and complex environmental effects like rain or debris. How do you manage the performance budget without killing the artistic intent?
This is where the role of a lead or a senior artist becomes critical. The first thing I do is establish a hierarchy of importance based on the story. Not everything in the frame needs the same level of detail. If the emotional core of the shot is the character's expression, then the face gets the highest polygon count and the most complex shaders. The explosion in the background, while visually impressive, doesn't need the same resolution as the foreground elements. I rely heavily on level of detail, or LOD, techniques. I'll simplify the geometry and textures for elements that are distant or obscured. I also work closely with the director and the technical directors early on to set hard caps on polygon counts and texture sizes. We can't just wing it with a scene that complex or the farm will just crash. I use profiling software to identify exactly where the bottlenecks are. If the shaders on the environmental debris are eating up 40% of the render time, but only contributing 5% to the visual quality, I'll optimize those shaders or simplify the geometry. The goal is to maintain the visual impact while keeping the pipeline sustainable. It's a constant negotiation between the perfect image and the renderable image.
Let's pivot the character work, but specifically non-human entities. When you're animating something like an insect or a quadruped, you can't just apply human kinetics. What are the paramount technical considerations there?
You're absolutely right. The biggest mistake is trying to map human movement onto a non-human rig. For insects or quadrupeds, the focus has to be on anatomy and biomechanics. For an insect, you're dealing with an exoskeleton. The joints don't bend like skin and muscle, they're more like hinges and plates. The rigging and skinning have to reflect that. You can't have soft deformations where there should be hard shells. Weight distribution is another huge factor. An insect has a very light, segmented body, so its movements are often twitchy and rapid. A quadruped like a horse or a dog has a completely different center of mass. You have to study how the weight shifts from the hindquarters to the forelegs during a stride. If the weight doesn't feel right, the character will look like a human in a costume. I also pay a lot of attention to secondary motion. For an insect, that's the vibration of the antennae or the flutter of the wings. For a quadruped, it's the swing of the tail or the jiggle of the skin around the neck. These details are what sell the realism. I always insist on using real-world reference footage, not just looking at other animation but looking at actual animals, to ensure the timing and weight are authentic.
I want to touch on some of the environment and background work. Let's talk about matte paintings. In a modern VFX pipeline, when is it most appropriate to use a matte painting instead of a full 3D environment?
A matte painting is still an incredibly powerful tool because it allows us to create massive, detailed environments that would be computationally impossible or prohibitively expensive to build in 3D. I'd use a matte painting when we need a highly detailed backdrop that doesn't require significant camera movement or interaction. For example, if we need a futuristic city skyline in the far distance, there's no reason to model 10,000 buildings. A high-resolution digital painting integrated into the scene is much more efficient. They're also great for extending sets. If we filmed on a small physical set but the script says the character is in a vast cathedral, we use a matte painting to fill in the rest of the architecture. However, the key is knowing when it's not appropriate. If the camera is flying through the city, a flat matte painting won't work. In those cases, I'd suggest a 2.5D approach, where we project the matte painting onto simplified 3D geometry or a full 3D build. But for those wide, epic establishing shots, a matte painting is often the most artistic and efficient choice.
Let's get into some rigging troubleshooting. You've probably run into null space in a rig before. For the sake of the interview, can you explain what that is and why it's something we need to avoid?
Null space in rigging is essentially a dead zone. It's a situation where a joint or a control exists in the hierarchy, but it has absolutely no influence over the deformation of the mesh. This usually happens when a joint's transformations aren't properly linked to the skin weights, or if another joint has completely overridden its influence. From a production standpoint, null space is a nightmare because it adds unnecessary complexity. It bloats the rig, making the files heavier and the viewport slower. More importantly, it confuses the animators. If an animator grabs a control and nothing moves, or if it moves but the mesh doesn't follow, they lose trust in the rig. It can also lead to unpredictable deformations or pops when the rig is pushed to its limits. A clean, professional rig should be lean. Every single control or joint must have a clear, direct purpose in how it deforms the mesh. If it doesn't contribute to the final look, it needs to be purged.
That's a good lead-in to some technical troubleshooting. Imagine you have a complex rendering issue. You're seeing lighting discrepancies across multiple assets, and you suspect it's a coordinate system or scale inconsistency. How do you approach that?
That's a classic pipeline headache. My first step is to verify the coordinate systems of every asset in the shot. I check the handedness, whether the asset was created in a left-handed or right-handed system, and I confirm the apaxis. If one asset is Y-up and another is Z-up, you're going to get flipped normals or lighting that hits the object from the wrong direction. Next, I inspect the scale. Scale inconsistencies are a huge cause of lighting errors, especially with specular highlights and shadow softness. If an object is scaled by 0.01 in one app and 100 in another, the light calculations might be off. I'll use diagnostic tools like wireframe overlays or normals visualization to see if any faces are flipped or if the geometry is skewed. If I'm still stuck, I'll isolate the problem. I'll render the assets individually in a neutral environment. If asset A looks fine alone but breaks when asset B is introduced, I know the issue is in the scene merge or the global coordinate space. I'll then standardize everything to a single master scale and axis before re-importing.
Let's talk about the polish phase. What is the main function of a cleanup pass in the VFX pipeline? What specifically are you looking for during that stage?
The cleanup pass is all about refining and polishing. It's the final filter that ensures the shot looks seamless. By the time we hit cleanup, the main animation and FX are mostly done, but you'll often find artifacts. These are things like jagged matte edges, slight color mismatches between the CG element and the live-action plate, or tiny tracking jitters that only become apparent at full resolution. During a cleanup pass, I'm looking for any tells that scream this is a visual effect. I'm checking for edge bleeding, ensuring that the integration of the CG object into the plate is perfect, and fixing any flickering in the renders. It's also where we handle the fine-tuning of the compositing, making sure the grain and noise of the CG match the original camera grain. The goal is to move from this looks good to this is invisible.
I want to go back to animation for a moment. Let's say you're reviewing a shot and you notice significant jittering when a character moves rapidly. What's the most likely technical cause and how do you troubleshoot it?
Jittering during fast movement is almost always a motion blur issue. If motion blur isn't applied, or if it's applied incorrectly, the eye perceives the movement as a series of sharp, disjointed snapshots rather than a fluid motion. This creates that stuttering effect. Another possibility is a frame rate mismatch. Maybe the animation was keyed at 24 FPS but the project is outputting at 30 FPS, or there's an inconsistency in the frame timing. To troubleshoot, I first check the render settings to ensure motion blur is actually enabled and that the shutter angle is set correctly for the look we want. If that's not it, I'll dive into the animation curves. I'm looking for sudden spikes or kinks in the graph editor. If there's a single frame where the character jumps a huge distance and then snaps back, that's going to cause a jitter. I'll smooth out those tangents. Finally, I'll check the rig for any instability in the skinning. Sometimes a vertex is weighted to two opposing joints, and as the character moves fast, that vertex vibrates between the two.
Let's move into some fundamental concepts for the sake of completeness. UV unwrapping. For those who don't know, what is it and why is it absolutely necessary?
I like to explain UV unwrapping as the process of taking a 3D object and flattening its surface into a 2D layout. It's exactly like taking a cardboard box and unfolding it into a flat piece of cardboard. Since textures are 2D images, like a JPG or a PNG, the computer needs a map to know exactly which pixel of the 2D image corresponds to which point on the 3D surface. Without proper UV unwrapping, the texture has no guide. You end up with stretching, where a texture that should be a circle becomes an oval, or distortion, where the texture just looks smeared. In a professional pipeline, clean UVs are essential for maintaining a consistent texel density. If the UVs are poor, the model will look unrealistic no matter how good your texture painting is. It's the bridge between the 3D geometry and the 2D art.
We've talked about cloth and rigging, but what about fluids and interaction? What are the specific challenges associated with simulating interacting elements, like water bouncing off a metal surface?
Interacting elements are challenging because you're dealing with two entirely different sets of physical laws. In the water-on-metal example, the water is a fluid, it's deformable, it has surface tension, and it follows fluid dynamics. The metal is a rigid body, it doesn't deform, but it provides a hard collision surface. The simulation has to handle the collision detection with extreme precision. If the collision mesh is too coarse, the water will leak through the metal or jitter on the surface. Then you have the energy transfer. How much of the water's momentum is kept versus how much is deflected. You have to model the splashes and ripples realistically. And then there's the rendering. Water is reflective and refractive, while metal is typically specular. Calculating how the water reflects the metal and how the metal reflects the water, all while the water is moving and changing shape, is incredibly resource-intensive. It requires a massive amount of computational power to get the particle resolution high enough that the water doesn't look like a bunch of floating blobs.
I want to pivot to a more conceptual question. Beyond just making a shot look good, what is the narrative purpose of exceptional visual styling? Why does it matter from a storytelling perspective?
This is my favorite part of the job. Visual styling is essentially a silent narrator. It's a visual language that communicates themes and emotions to the audience without needing a single line of dialogue. If we use a dark, desaturated color palette with high contrast, we're subconsciously telling the audience that the character is in a state of turmoil or that the world is oppressive. If we use fluid, exaggerated animations, we're conveying a sense of freedom or perhaps chaos. Exceptional styling guides the audience's emotional journey. It can make a character feel more alien, more heroic, or more fragile just through the way they move or the way the light hits them. When the visuals align with the core message of the story, the experience becomes immersive. It's not about eye candy. It's about using every visual tool available to deepen the narrative and make the story more memorable.
Let's get back to the basics of animation timing. When you're discussing timing with a junior, how do you explain spacing?
I tell them that if timing is when an action happens, spacing is how it happens. Spacing is the distance between the poses from one frame to the next. It's what actually controls the speed and acceleration. If you have tight spacing where the frames are very close together, the movement feels slow, controlled, and deliberate. If you have wide spacing where the object jumps a large distance between frames, the movement feels fast and dynamic. Proper spacing is how we sell weight. If a heavy boulder falls, it starts with very tight spacing at the top and gradually widens as it accelerates due to gravity. If the spacing is linear, the boulder looks like it's floating in space. By mastering spacing, we can make an object feel like it weighs 10 tons or like it's as light as a feather, all without changing the overall timing of the shot.
I want to give you a specific scenario. Imagine you need to simulate the interaction between two entirely different materials, let's say burning wood and wet cloth. What physical parameters would you need to model to make that look realistic?
That's a complex interaction because you're dealing with thermodynamics and chemistry as well as physics. First, I'd focus on heat transfer. I need to model how the fire's heat moves from the wood to the cloth. This involves conduction through direct contact, convection from the hot air rising, and radiation from the flames. Second, I have to account for moisture dynamics. The cloth is wet, so it won't ignite immediately. The heat from the wood will first go into evaporating the water in the cloth. This creates a cooling effect on the surface and slows down the burn. I'd need to model that phase transition from liquid to gas. Third, I'd look at material properties like thermal conductivity and ignition temperature. The wood and the cloth will react differently to the heat. Then there's the chemical side. The combustion of the wood releases gases and smoke that will interact with the fibers of the cloth. Finally, I'd add physical deformation. As the cloth dries and then chars, it will shrink and warp. If you just put a fire texture on the cloth, it'll look fake. You need that shrinking and charring to sell the interaction.
In terms of software, for compositing VFX shots, what is the industry standard and why?
That would be Nuke by Foundry. It's the gold standard for a reason. Unlike layer-based software, Nuke uses a node-based workflow. This is crucial for VFX because it allows for a non-destructive, highly flexible pipeline. You can see the entire flow of the image from the raw plate through the keying, tracking, and color correction, and you can branch off that flow to try different versions without starting over. Nuke is incredibly powerful for handling high-resolution footage and integrating CG elements with live-action plates. Its toolset for deep compositing and its ability to handle complex transforms make it indispensable in a high-end studio environment. Most major films you see today are put together in Nuke.
Let's talk about a different medium, frame-by-frame painted animation. How do you ensure temporal coherence in that workflow? How do you stop it from looking too flickery or jumping around?
Temporal coherence in painted animation is all about consistency across the timeline. To prevent flickering or jumping, I maintain a very strict reference for lighting and color. I often reuse elements from previous frames or slightly adjust them to ensure the palette doesn't shift unexpectedly. I also plan my motion paths very carefully. If the movement is too erratic, the coherence breaks. I rely heavily on onion skinning, which is where you can see faint overlays of the previous and next frames. This allows me to align the new drawing precisely with the old one, ensuring the speed and direction of movement remain steady. I also try to limit drastic changes in shape or volume between consecutive frames. If a character's head suddenly grows by 10% in one frame and shrinks back in the next, that's where you get that jarring, unstable look.
Final technical scenario. The camera is moving very quickly past an object. What visual technique can we use in post-production to enhance that sense of motion blur if the render didn't capture it perfectly?
In post-production, I would apply a directional motion blur effect. This is a way to simulate the natural blur that happens when an object moves rapidly across the sensor. The key is to align the blur exactly with the direction of the camera's movement. I'd adjust the intensity based on the perceived speed. The faster the movement, the more elongated the blur. This is a great way to sell the illusion of high speed without having to go back to the render farm for a full re-render, which can save a huge amount of time and money.
Last one from me. You're tasked with a shot that requires a massive crowd of background extras. How do you pipeline this so you aren't rendering every single character individually?
For a large crowd, you have to move away from manual animation and into procedural systems. First, I'd build a library of a few base character models with variations in clothing, body types, and basic animations. This gives the illusion of a diverse crowd without needing 100 unique models. Then I'd use a crowd simulation tool to populate the scene. I would define the general paths, behaviors, and interaction rules, like don't walk through other people, and let the tool handle the distribution of the characters procedurally. To make the rendering feasible, I'd use instancing or geometry caching. Instancing allows the renderer to load one model into memory and simply repeat it across the scene with slight variations in scale or rotation, which drastically reduces the memory overhead. Finally, I'd composite the crowd in layers. I might render the foreground extras at a higher quality and the distant crowd as a lower resolution pass, then blend them together in Nuke to match the environment's lighting and color.
That's a very comprehensive answer. I appreciate the level of detail you've provided today. It's clear you have a strong grasp of both the technical and artistic sides of the pipeline. I think we have everything we need for now. We'll be in touch soon regarding the next steps.
Thank you very much. I really enjoyed the conversation. I look forward to hearing from you.